In this video, we're going to learn how to graph logarithmic functions. Now on the left, I put several facts about logarithmic functions, but as I go through the examples, I'll refer back to these facts so we can use them in a more effective manner. So I'm going to start with a very basic function to graph, which is log base 3 of x. There's no transformations like you're going to see in the other two, just the basic log base 3 of x function. So in order to graph this, we're actually going to use a fun technique, which is rewriting y is equal to log base 3 of x into its equivalent statement, its defining function. Because y is equal to log base 3 of x, since the log is equal to the exponent the base must be raised to, I can write this as 3 to the y power is equal to x, which puts me in a situation of not picking x values to plug into the log function, but picking y values to plug into the exponential function to find those x's, since these two statements are equivalent. So I can just pick y values, plug them into the exponential function, so 3 to the negative 2 would be 1 over 3 squared, which gives me 1/9. So when x is 1/9, the logarithm is equal to negative 2. I plug in negative 1 into my exponential, 3 to the y here. 3 to the negative 1 is equal to 1 over 3 to the first, which is 1/3. So when x is 1/3, y is negative 1 for the logarithm. Plug it in 0, I get 3 to the 0. This gives me 1. So when x is 1, y is 0 for the logarithm. 3 to the first is 3. So when x is 3, y is 1. And 3 squared is 9. So when x is 9, y is 2. And when I go to plot these points, I'm going to start with my my x-intercept, where x is 1 and y is 0. And then these points right here, when x is 1/3, y is negative 1. And when x is 1/9, even closer to 0, y is negative 2. And we discussed in the previous lesson that the domain for these functions is 0 to infinity. So you're actually going to see a vertical asymptote form as I follow those points down the y-axis. So these functions have a horizontal asymptote at the y-axis typically. And the equation is x is equal to 0. It's a vertical line. Now continuing to graph the other points, I go over to 3 and y is 1. And when x is 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9, y is 2. And you'll see it start to grow, but slower and slower over time, but always growing upwards, which causes the range to be all real numbers, because it goes down over here on the left, and it slowly goes up to the right over time. So my domain for this function is 0 to infinity, and my range is negative infinity to infinity. So that's how you basically graph a logarithmic function. Now when you have transformations, you'll plot the basic logarithmic function first. So here, if I were to strip away the transformations, so that 3 and that -1, I'll end up with this y is equal to log of x. And if I try to write out its equivalent statement, its defining function, you'll notice that I don't have a base there. Well, this is known as a common logarithm. You're not given a base. That base is assumed to be 10. So its equivalent statement is x is equal to 10 to the y. So I'll just pick -1, 0, and 1. I'll start with the y-intercept. 10 to the 0 power is 1. So when x is 1, y is 0. Then for 10 to the -1, that's also known as 1 over 10 to the first. So when x is 1/10, then y is -1. And when y is 1, x should be 10. So those 3 points are my basic points. And now I'm going to plot this in a dashed green line. So It doesn't stick out as I apply the other transformations, but also notice that I'm counting by 2's on my axes. So when I plot 1, 0, that's in the middle here, between 0 and 2, and 1/10 is butted up against the y-axis at -1, which would be between -2 and 0. And then my other point's at 10, 1, so all the way over to 10, and then up 1, which is between 0 and 2, giving me this function. Now let's apply these transformations that are taking place. So the first transformation I notice is 3 log of x. I'll save the -1 for later, but this transformation is a vertical stretch by a factor of 3, which means that every y value is going to be multiplied by 3 to find its new location. So the y value here at the y-intercept won't change, but this one here at 1/10 -1, if I multiply -1 by 3, it'll stretch it downwards to -3. And the other point here that's at 10, 1 stretches upwards to 10, 3. Cause this function to stretch out a little bit more and reach a little bit higher than it did before. Then lastly, the last transformation is to apply the -1 to the x, which would be a horizontal translation right 1 unit. So every point will move to the right 1 unit, including the vertical asymptote, which was at 0, but now when it moves to the right, it goes to x equals 1. So moving every point to the right 1 shifts this point down here at 1/10 -3 over to what looks like 1 1/10 -3. The point at 1, 0 goes over to 2, 0, and the point here at 10, 3 goes over to 11, 3, giving me this as my final graph. So reading out that graph, I can see that my domain is not from 0 to infinity. Since I've shifted to the right, my domain now goes from 1 to infinity. My range is still all real numbers. And my horizontal asymptote, which I'll use HA for short, is x equals 1 this time. So some things to notice about the very basic function is that the 3 basic points you'll use will be 1, 0, that's usually your x-intercept, which helps, b1, the base, and then y will be 1, and then the reciprocal of the base for x and y will be -1. Those are very common points you'll want to graph. Now for this last example, I have f of x is equal to log base 1/4 of -x minus 2 plus 3. But the key thing to notice here is I have a negative in front of that x. Which I need to factor out of those two terms to see what my true horizontal translation is. And then I can continue forward. But I'm going to actually graph y is equal to log base 1/4 of x to solve this. And now when you have log base 1/4 of x, that can also be read as 1/4 to the y power is equal to x. So since this base is not a whole number like I've seen before, I'm going to use a few more y values to make sure I don't miss anything. So first, 1/4 to the 0 gives me 1. So when x is 1, y is 0. So very similar point we've seen before. Now when y is 1, x becomes 1/4. So my point now, when I go to 1/4, it doesn't go down. It's actually going to go up to 1 right there. And when y is 2, I get 1/4 squared, which is 1/16. So even closer up against the axes, I'm still climbing up as I get closer to that y-axis. Now when I go in the opposite direction, I do 1/4 to the negative 1 power. The negative exponent typically takes the reciprocal of the number. So the reciprocal of 1/4 is 4. So 1/4 to the negative 1 is equal to 4. So when x is 4, y is negative 1. So 1, 2, 3, 4. Y would be negative 1. And then for 1/4 to the negative 2, that would be the reciprocal of 1/4 squared. So 4 squared, which is 16. So when x is 16, y is negative 2. I can't fit that one on the graph, but we can already see this graph form. Which looks upside down for what it normally does. Normally it's going upwards. This one's decreasing over time. So you'll notice when the base is between 0 and 1, it's a decreasing function. But when that base is 1, it's an increasing function. But let's apply the transformations. So these transformations went to that graph. And these transformations down here will go to this graph. We'll start with f of x is equal to log base 1/4. And we're just going to address the negative on the inside of the function first. This would be a reflection in the y-axis. It's a horizontal reflection. So every point is going to reflect across the y-axis. To look like this. So you'll see it's now reflected across that axis. And then we're going to apply the translations. So log base 1/4 of negative of x plus 2 plus 3, which this comes with two transformations. The plus 2, which we thought was minus 2 before, indicates a shift to the left instead of the right. So I go left 2, and then the plus 3 on the outside means I go up 3. So every point goes left 2 and up 3 to get to my final graph. So left 2, and then up 1, 2, 3. Left 2, up 3. And now even this vertical asymptote that was at x equals 0 is also shifted left 2. So now instead of being at 0, it'll be at negative 2. And I usually like to graph the asymptote when I'm doing these points that are really close to the y-axis. So they kind of give me a point of reference as I plot the final points. So here, as I go left 2 and up 3, I'm about right there. And then left 2, again, I'll right up beside this asymptote, and then up 3 puts me about right there. Give me my final graph to be right here. So if I were to write out a few statements about this graph, its domain, it's going to be a bit different because now it's not going to go from like 0 and then off to infinity. It's going to go from negative infinity all the way to negative 2. The range will continue to be all real numbers, so negative infinity to positive infinity. And my horizontal asymptote, HA for short, is now x equals negative 2. And that is how you graph logarithmic functions.